Yeah, so hi everyone. So I will try to give you a bit some context about multi-messenger observation with gravitational wave. So here I will focus on gravitational wave event that includes a binary system that includes a neutron star, because we hope to have different sensors from this phenomena, gravitational wave on one side and electromagnetic sensors. So first, the kilonova, that we can have a witness of it just at the collision and after, and the GRB, that is a more relativistic, comes from a more relativistic zeta, much more beamed than the kilonova, and it's a completely different phenomenon. So far there have been only one clear kilonova detection that was, from my point of view as an astronomer, very easy because the source was of 40 megaparsec. And this kilonova was revealed thanks to gravitational wave detection that asked the astronomer to look in a region of 40 degrees square. So for some of you, you don't understand what that means, but basically there were 10 galaxies in this region. So if you have telescopes with a narrow field of view, you point 10 sources, and then you got your kilonova, because the brightness of the kilonova was accessible by 50 centimeter class telescopes above a few hours after the gravitational alert. So for the standard gravitational wave event, it's not like that, and I will try in my talk to give you all the point of progression that we have done to follow up and make this multi-messenger detection. So to have to are able to understand the behavior of dense matter and physics of the compact objects, you need to deal with for me, very compartmented physics domain of research. So as just Geert presented, our team Dietrich, the idea is to combine this different information in a multi-physics modelization to extract some figure about the properties of the neutron star or black hole or the binary systems and post-merger, and also derive some properties for all the topics associated to nuclear physics or cosmology. But for that, you need to have data from gravitational wave and electromagnetic. I need to collect the good data, so at early stage, because the model of the kilonova and how the air process is done is better to have the beginning of the story, right, and to start the book in the middle of the story. So to do that, you need to go as fast as possible and to have both LIGO Virgo online, that is not actually the case, and instrumentation on the electromagnetic side. So that's why you need to keep in touch with astronomer. And finally, you need to have person able to pre-process the data and to validate them, because there are a lot of bias in data from the telescopes, right? The sky is not that clean as gravitational waves, so you need to collaborate with a person from time domain, from classical astronomy, and of course gravitational wave physicists. And in this very diverse community, we are using more and more machine learning, and at different steps of the pipeline. So I will give you two examples. One, for example, for astronomy is to understand if the new point, a new point that we detect in our image, is it astrophysical or an artifact? For that, we use machine learning, or to have a rapid estimate of the properties of the progenitor based on gravitational wave. This is what, for example, University of Amsterdam is trying to do, to understand if there is how much is the scientific opportunity for the electromagnetic counterpart. So as just Geert presented, in LIGO Virgo we detect 90 events, and here in my talk I will focus more on the event that we have the most, will more probably detected the EM counterpart of that entire neutron star. And we start with all the chain. From first, we need to have detection of gravitational event and be able to send, when we have detected in Virgo, to send the alert to the EM community. And here I would like to show how it has been evolved since 2015. So at the beginning, so we need to send alerts, and now we are able to send alerts within minutes, 7 minutes exactly in average for the last run to the astronomical community. And so in O1, so this is a region that we have our detection and alert. So you have the distance of the events versus the credible region, so the search area that the astronomer needs to cover to detect the EM counterpart. So in black, you have the black hole. So we were detected in O1 black hole around 1000 megaparsec, 1 gigaparsec. And then in O2, we still populate that region, not well localized and still far away. There is the arc layer of 17 and 17. And in O3, you see there are other colors because we detected candidates of neutron star black hole and binary neutron star. They are not well localized because here is a big search area. We do not, unfortunately, we have only one outlier here that was well localized. And in the second part of the run, it was exactly the same. So in terms of capability of observation, so O3 was followed similarly to O2 with 100 groups covering neutrino, high energy facilities, and all the multi-wavelengths coverage. Most of the partners were optical, but they are individual teams. And so it's very difficult for optical facility with groups of astronomers done by like 10% to follow up all the candidates that we have and maybe find the kilonova. So mostly, in fact, they were focusing, which is natural, on NSBH and BNS events. And only persons that gather, collaborate, making larger groups, consortium, like Master, Gamma, and Growth, they were able, in fact, to absorb all this flow of alert event at O3. So I don't talk about O4, and I will come back to that in a minute. Whereas blind search that just like compares the archival data at the time window and in spatial coincidence with gravitational alert, they run their analysis for all the event, of course. And here is a schema that shows you that, in fact, there are some disparity between the different groups, because some of them, they are very good at spectroscopy, but they have limited time compared to people that have much more access to a lot of telescopes that can promptly observe after gravitational alert, but maybe do not have the deepness to detect kilonova at 2021 magnitude. So there is also a problem in terms of localization, because it is one of the big challenges to detect the counterpart of binary neutron star coalescent. This is the sky map, the sky coverage. It is the candidate for the BNS that cover a quarter of the sky. However, it was the second popular event, followed, in fact, during O3. 118 GCM reported. So the question that you can have is what has been the most popular event, and it was 1914 that finally was classified from the gravitational wave point of view as a BBH merger, and it was the most popular. So why? Because its search area was around 23 degrees squared. And so 1, 2, and the third, fourth, and fifth candidate most observed by the partner, by the astronomer, were candidates that were not confirmed in our LIGO Virgo O3b catalog paper. So it shows you, in fact, that we have resources, we can follow up, but maybe there is some misunderstanding about the best, in fact, alerts to follow up. And this is very problematic because we have limited resources to follow up. And we stop observation from our colleagues that do exoplanet and something else. So if we want to keep this this energy in this boom of gravitational wave astrophysics, we need to keep going and have the best indication to indicate to the astronomer what to do. So here is some reference, I will skip that, but from a different partner. I try to put a large diversity from all the continents, and I will look for the future for O4. That's I think you know, but the run is postponed to March 2023 now. Bad news is that the sensitivity for CAGRA is only 1 megaparsec. For Virgo, officially still from 80 to 115 megaparsec. So we will have by a factor of three times more events than O3 in O4, and almost 1 detection per day. So now I make a little game. I compare to the publication that we have in LIGO Virgo in 2015. We were supposed at that time in 2015 that in 2022 we're gonna detect much more BNS. Of course, the range is unprecedented at the time in 2015 because there was no BNS detection. But we were promising in 2015 to have more than 20 candidates localized within 5 degrees squared. And if we take the last sensitivity of our instrument and we make prediction, so this prediction comes from Patron 2021. In fact, the medium scale localization area is not about 5 degrees squared, is about 1,800 degrees squared. So you see there is a big difference. And why it is 1,800 degrees squared is because our different detectors, they have very now different sensitivity compared to Livingston, to CAGRA, and so we will detect much more events, but a large fraction of the event won't be well localized. So we will not solve a problem to find better the kilonova. And so it's very important to take into account this evolution of our prediction, because if we say, okay, I would like multi-messenger, I would like to know which search area I need to cover to understand my rates for multi-messenger detection, that I can. So this is a little game that we do with Michael Kosling to understand how we can better estimate, for example, H dot with multi-messenger analysis, or for example, the radius of the neutron star. And so you see that if we think once again of 2015, and if me, an astronomer, I want to make a new instrument dedicated to gravitational wave follow-up, and I say, okay, in 2022, the size will be around 10 degrees squared. In 2015, I will have chosen another instrumentation than the reality. So in fact, there is a big disconnection now with new instruments that in fact are not well designed for the actual gravitational wave alert properties. However, there are some new telescopes in the EM community that can help to have this multi-messenger detection, and there is a boom in wide-field imagers. So you think, of course, about LSST, but there are a smaller project, farm of telescopes, as GO2, as Turbo, etc., etc. In another wavelengths, we will have SWAN, a French Chinese project that is able to deliver the gamma ray trigger to the community. And I think that in the future, we will have already some tentative of wide-field near-infrared. Why? Because you can have more time to detect the kilonova, because the near-infrared kilonova peak days after compared to optical, and maybe UV. There were some tentative in UV, and also the big problem is also to classify, in fact, many candidates in this search area of gravitational wave, and so that's why there are some starting projects about low resolution spectroscopy. So However, there is still a disconnection between all these individuals compared to LIGO Virgo, that is a massive collaboration, let's say. And so even if there are still not wonderful dedicated instrumentation to gravitational wave follow-up, the group, they observe the same fields, the golden tide, that we call the golden area. And so there are some duplication in terms of observation, and it's not optimized, in fact, take it globally to build this multi-messenger sample with gravitational wave. However, we are actively working in LIGO Virgo and in the astronomical community to try to make this path smoother. And so I will start with improvement from the LIGO Virgo side about the alert. So we will still, in LIGO Virgo, deliver the same type of alert as in O3. So based on different pipelines, and with also events that are not correlated with neutron star coalescence. And we will deliver our alerts within minutes and in O3, and maybe even a bit timely. We will give the detail in September, and we will also deliver to the astronomer community early warning alerts, so prior to the merger, so that maybe some astronomer needs to store, in fact, the data as some of the radio facility. And we will deliver this alert not only in GCN, that was a classical broker to listen to our alert, but also to other much more modern brokers using other format of alert like JSON. So we also work on trying to give better rapid estimate properties, especially the sky map. And I would like to highlight the work on Pierre-Alexandre Durian, who is doing his PhD with me. And I've worked on the rapid sky localization algorithm and its accuracy, especially to tune the fuge factor, that is a factor that is applied prior to perform the localization map, to try to compensate with the discrepancy between the waveform and the real signal. And we see that only this fuge factor has a big impact in the sky localization. So if you take a fuge factor, so it's a constant, right, on 0.75 or 1, you can double your search area. So it's not the same consumption in terms of observation, only with this fuge factor that is just a constant in our pipeline. And so when we were looking if the fuge factor that we use in O3 was the best one, and we thought that it was not, because it was only optimized for one pipeline, whereas we have different search in LIGO Virgo. So this is something that we are actively working on. So now I move to the kilonova size. Sorry. Yeah, and how to detect the kilonova from the astronomical point of view. So once we have received the alert, we can rapidly scan the sky localization area or point some interesting target as potential host galaxy, as it was the case for 170117. But we have candidates that we need to understand whether or not they are related to the gravitational wave events or not. And this takes time. And once it is done for only 1717, we could have, follow-up. So to make this strategy come through, there is a question about rates over time, and you need to have large, you need to have access to a lot of telescopes to be able to promptly observe the good portion of the sky. But you need also to have in your community some gravitational wave physicists that can help to make the filtering of the alert, and it will be more and more important when there will be more and more detection, alerts, but also help to drive you for the science once you have the data. And you need to have, if it is a question of neutron star, nuclear physicists that help also in this consortium. So remember my slide in ecosystem, I just defined that I mean, I do not recommend to be alone and just like follow up as a pure astronomer. And that's why I built this consortium GRANDMA in 2018, starting in France. Now it's composed by 90 scientists, as I said, from nuclear astrophysics and physicists, gravitational physicists, astrophysicists, and astronomer. And we are running a project, and we are present now in 18 countries. And we have telescope access because this is one of the ingredients to success to perform multi-messenger detection with a strong focus in Eurasia to try to quickly observe when there is a gravitational alert or in case of kilonova candidate independently from LIGO Virgo. But having this telescope, behind the telescope, there are people. And so we observed that in this, particularly in Asia, there was not too many people that have access, in fact, to our gravitational wave knowledge. And so that's why behind them there is a large pedagogic and effort to include, in fact, to have this diversity around our multi-messenger community. And so GRANDMA is really also a prototype for using the diversity as a start for our group to have higher innovation, to try to be much more universal. And here I show all the women that are in our consortium. So this diversity needs to be managed, and this is part of our hard task for the consortium. For now, we practice with GRANDMA the first time in O3 when we observe 90% of the O3 alerts. So it is one, as I said, of one of the most active networks and active astronomical community in O3. We really focus our objective on really promptly observe. So we observe up to 50 minutes after the gravitational alert, and we're able to scan per alert around 200 degrees square. This is all our observations that we made during O3. However, we need to progress in terms of sensitivity because our average was 18 magnitudes, and it was not enough. It was not for faint kilonova, and so we are progressing in that stage to add new groups that have better sensitivity or make longer exposure to reach the sensitivity, because we can't constrain the ejecta mass, for example, for a BNS with this sensitivity. Okay, so beyond that, for preparing O4, we are not enough, we don't have enough resources to build all the pipeline in GRANDMA for the observation, for the data reduction of all the telescopes, for managing the observation, for filtering the candidates, etc. That's why we connect with various groups that develop tools in all over the world, and especially with growth, with Caltech, to connect our tool and to develop some tools for observation of multi-messenger events. And I would like to highlight Sky Portal, which is a data science platform that is not only a visualization tool and say, oh, there is this alert and this coincidence with the gamma burst, etc. It is also that we can upload our photometric results and also have some rapid estimate of kilonova. We can apply rapid modeling to see if the transient looks like a kilonova or not. And this tool, I think, go beyond the actual visualization tool that usually people have. Another progress that we have massively investing in GRANDMA, lead by Tim and Peter Ponk, is numerical multi-messenger analysis. I won't come back to that because Tim presented the framework. And also we have another independent multi-messenger analysis that was just presented by Geert just before, because from the astronomical point of view, we like to have independent model because they don't stick on the same aspects. And we are developing also citizen science because we think that there will be a time that it won't be enough sufficient to have observation from professional, and it costs less and less to have adequate telescopes in the market. That's why we are developing citizen science for observing multi-messenger events. And if you know astronomers, they can connect to our site and participate. So now I will try to finish in 2 minutes about the preparation for O4 that we do in GROMA. So first, our program in GROMA is focusing on kilonova and gravitational events. That's why we started between O3 and O4 to seek for kilonova candidates that were detected from ZTF survey for the Zwicky Transcend facility, and try to classify, in fact, the ZTF Transcend facility, adding additional photometric points to the point from the survey, because the point of the survey is not a very good guidance. It's 1 point every 3 days. So if you have a kilonova that's fading, I mean, at this magnitude within a day, then you don't see it. So we try, as it is shown in the graph, as this is a light curve, right? We try in red, these are the point of GROMA, and you see between two ZTF points, we can complement, in fact, the light curve of ZTF to really classify the transient and maybe find a kilonova. And much more recently, like months ago, we also prepare, because we need to prepare all our tools, as I said, to be ready for O4. We seek for kilonova with GRBs, so not with optical survey as just before, but with GRBs, and to train how to actively respond to alerts. And among these 2 months, we observe 11 gamma rebursts. And among these 11, we have detected independently 3 afterglow with 2. For 2 afterglow, we have minutes detection just after the alert as 220427A. This is remarkable compared to other, and we try, to complement so our early detection with deeper facility to be able for O4 to have all the light curve at a certain point of kilonova. So I would like to thank you to have listened to me. I make just a recap. So first, for the alert provider, for me, for the kilonova, there are 2 channels. One is the LVK. That takeaway message is that finally the sky localization area in O4 won't be so good. We need to be prepared to have the same strategy as in O3. We have another channel which is like orphan kilonova in surveys as ETF that just rise, that we can maybe extract some properties about that. For the follow-up, now we have the proliferation of farm telescopes and maybe the rise on near infrared wide field of view. And the standardization and interoperability of tools is very hard. That's why we need to work in advance prior to observation and not to try to sell to someone else, because it's very difficult and it's not universal. And to conclude, I really think that for multi-messenger observation and detection and analysis, we need to make this like a consortium like GROMA with both of you, nuclear astrophysicists and gravitational physicists and astronomer. It can work because it works in GROMA. Well, so thank you.